Good morning and welcome to another Micrographics webinar. I'm your host Carl van Rooyen, and today we will be going through Autodesk Fusion and how AI is driving workflows within the Fusion environment. As mentioned, my name is Carl van Rooyen. I'm an application engineer with Micrographics. Been with the company for over 10 years, working with Inventor and Fusion as the two main products, along with Vault. And as mentioned, today's focus will be on Fusion. We'll jump straight into the agenda. We'll start off with an introduction to AI in Autodesk Fusion as an overview, having a look at where it is being used, and then we will more specifically go into generative design with AI, having a look at the generative design studies within Fusion, and then we will have a look at AI-powered 2D drawing automation. Then we'll close off with a summary and Q&A. So as mentioned in this webinar, we will explore how AI technologies are transforming workflows in Autodesk Fusion, from generative design of 3D components to 2D drawing automation. Fusion is leveraging AI to empower users to be more efficient, to create more accurate designs and give them time to be innovative. And whether you are exploring alternative designs or automating the tedious drawing process, so we're having those two areas that AI is helping. AI is at the forefront of enhancing your productivity. So we'll be going through those two main areas where that AI is enhancing the productivity, and we will be looking a little bit deeper into those. And we're going to jump straight into generative design. So having a look at generative design, we have two separate study types that can be done. The main study type is the structural component study type, and then there is fluid path, which is a preview sort of technology that is in the works. They are improving and working on that. So having a look at this with generative design, how does it help? Generative design basically is a game changer in Autodesk Fusion. With the AI-powered algorithms in the background, engineers can now explore design alternatives that they may not have actually considered themselves. So to break it down, what we're looking at here is optimizing structures for weight, material, and performance, but letting the algorithms, the AI, calculate and create that geometry for us. And now there's also the fluid path preview. You can also optimize a fluid path through a component to reduce the pressure drops through that component, in turn improving the performance of that design. So the use of AI in design leads to faster iterations where we can get multiple outcomes and we can be more innovative with the designs. So as mentioned here, we'll explore how this tool can help you streamline your design process, save costs, and also improve design efficiency. Now, if you have not been exposed or seen what generative design is, I'll give a quick explanation. On the left-hand side there, if we're looking at generative design for a structural component, we can see that we have an image there with a couple of different wheels. On the left-hand side, over here, we have the original design of a caster wheel, and we may need to look at reducing the weight of the caster wheel but keeping the strength the same. It may be for commercial airlines, and they need to reduce the mass of the catering trolleys. And so the design challenge here is to keep the strength but reduce the weight of the component. And so we'll go through the steps in generative design. We can see the second step there with the yellow and the red geometry, the green and the red geometry, that is showing the areas to shaft that will hold the bearings. And what generative design will do is it will create geometry to connect to those areas, but that geometry is created to withstand the forces that would be applied to the wheel. So you set this wheel up with fixing constraints and forces so that the software has a starting point to start calculating how much material is required. And during the process, you'll be able to specify how the part should be manufactured. So whether it's going to be machined, die cast, 3D printed, the materials that you want to explore as options, stainless steel, aluminium, titanium, and the generative design algorithms will create multiple iterations of the design, and you can then choose the best result that is going to work for your work case. In the case of fluid path, this is used to design components that will have a fluid flowing through them, and you're wanting to essentially reduce the pressure drop through that so you do not lose energy in the system. And by doing this, you create a more efficient component. So here we have an example of a valve, and we can see the fluid flow through that valve, and that path that fluid is taking is going to result in the least amount of pressure drop across that valve. So with AI-driven exploration here, we can see that we can use generative design to rapidly explore alternative design solutions, and we can use it to optimize for factors like weight, strength, and material usage. And here's a nice example. This is one that Autodesk push quite a lot. It is from General Motors. The bracket on the left-hand side is for mounting into the vehicle and attaching the seatbelt buckles to. And it's made up of 8 or more components, all pressed steel that have to be pressed individually and then welded or fused together. So there's quite a large production chain, value chain added to that. There's all the assembly process and the welding. Where on the right hand side, they've taken generative design and created a 3D printed bracket that is lighter and if not stronger than the original. And that is one single component. They've reduced down the value chain to basically just 3D print and fit in the vehicle. So this is a good example of a result with the generative design process. So generative design can give you fast iterations because the algorithm is giving you multiple outcomes. It gives you a whole lot of different results that you can then view. So we see how that AI reduces the time spent on manually iterating by generating hundreds of potential design alternatives. Now it says hundreds here, but it depends on how much input information you put in. So depending on how many materials you choose, depending on how many different loading scenarios you place down, that number of potential design alternatives will change. And this is all based on your user-defined criteria that you put in at the start of the study. So we can see just an example here. There's some recommended outcomes on the left. So we're seeing outcome 5, 6, and 8. And on the right-hand side, we see the first 3 outcomes, outcome 1, 2, and 3 there on the right-hand side. So here, once again, we're coming back to that bracket as an example. This generative design and AI helps to identify the most cost-effective and suitable design, balancing performance with manufacturing feasibility. So I'll come back to that. Manufacturing, welding all of these sub-assemblies together on the left-hand side to create this final assembly versus 3D printing one single component. So that generative design has those built-in functionality to choose your manufacturing process, the materials required, and this can help you reduce, let's say, material wastage or choose the correct or available manufacturing processes that you have. Let's say you can only 3-axis machine, so you would choose that and create your outcomes according to the 3-axis machining. So that is a overview there, a quick overview of generative design with AI from a structural perspective. what we'll do is we'll move into the fluid side next, and then we'll go through some examples, some basic examples of the process. So having a look at design optimization for fluid flow, we see here that generative design can be used to optimize the fluid path, as I mentioned, through a component to reduce pressure drop and essentially increase the component efficiency. So there's a nice little image of an example where we've got a valve with fluid flowing through the valve, and the yellow there actually represents a starting shape, a starting point, but the optimum flow we'll see is different to the actual shape that the designer had initially thought of using. So having a look at this, the fluid flow does allow us to enhance the efficiency of components that will have fluid flowing through them. So we'll move into the examples. So our first example here is one of Autodesk's examples that's inside of Fusion. So you can actually open this example up from the samples sections and have a look through this process as well. Due to generative design taking some time for outcomes to be calculated, I'm not going to go through this live in the demo. If there's time towards the end, I'll open it up in Fusion and we can have a look at the user interface in Fusion. But I've got a step-by-step here in the PowerPoint. So if we have a look here, this is a structural bracket. The goal or the design of this bracket is required to support a rod or shaft. On that bottom right hand side there, that red surface would support a shaft. It's bolted down using 4 bolts. So towards the back left of the design, we can see 4 bolts going through the component. And there are components that need to be avoided, hence why we've got this sort of uphill and then it comes back down. So there's that V shape underneath it to create clearance for other components. And if we look here, the material is steel and the starting mass is about 860 grams. And so that is what the designer came up with, but it's quite a heavy part. And so they're looking at that going, well, how can we reduce the weight of this component? And so we look at generative design, and what we can do in generative design is we can start the process by creating what we call preserved geometry. So that preserved geometry allows you to create areas that you have to have in the design. So basically what we have here, we've got 4 areas that will house the heads of the bolts. So let's assume we're using cap screws here. We've got some counter bores there for the cap screws to fit in. On the right hand side, we have the bearing surface for the shaft that is going to be held by the part. So that's our starting geometry. We need to give the AI something to start with. We need to give generative design that starting point. So we create this, what we call preserved geometry. Then to that, we add what we call obstacle geometry, areas where generative design should not create geometry. So we don't want anything there. That's areas to avoid. We need clearance for the bolts. We need clearance for other components. We can see the red shaft there. We need clearance for that shaft because that is a different component that will be supported. Then lastly, we can give it a starting shape. So here we see the yellow representing the design that the engineer came up with and said, okay, that's what I've started with and I want to then optimize that shape. And that is the geometry that you feed into the generative design. From there, you would then add your loads. So we can see that we have a load applied to the component as well as constraints. So we're fixing it down. We've got those 4 bolts, it's holding it down. So we need to feed that information in. We give loads, constraints, and we can also choose objectives. So we'll see that here we have objective. In this case, we want to minimize the mass of the component while we keep a safety factor of 2 at the lowest. So we're looking at a minimum safety factor of 2. But so generative design will remove as much material as possible, but stick to that safety factor. You can see there that we can also maximize stiffness. So if deflection is a worry in the component, we can maximize stiffness. There's also modal frequency, displacement, and buckling that can be optimized for. Then lastly, you can choose the manufacturing process. So for this example, it was said that we're going to create an unrestricted shape. Just create anything, the strongest bracket possible. We'll figure out how to make it afterwards. And then additive is checked there as well. And with additive, as an example here, we've got orientation. So X, Y, and Z. The part can be oriented in those three orientations to be able to 3D print using additive. Various other options there. We've got overhang angle and minimum thicknesses. So those will go down to the additive process for the printing and the possibilities of how that part can be printed. Then we have the three other options. Milling. So under milling, if we expanded that out, we would have various milling options: 2.5 axis, 3 axis, 5 axis machining. And that would generate components that can be machined using the selected milling criteria. We also have 2-axis cutting for like, let's say water jet or laser cutting, and then casting, which is a die casting process. It'll create a shape that is possible to be die cast. Once you've fed all that information into the software, you will then create the study. And this is where that information is shipped off to the cloud, and Fusion's cloud solver for generative design will go ahead and start to solve and create different outcomes. And so depending on the materials that were chosen for the component, and that's actually one thing I realize I'm missing here, is the material requirements. So you could have chosen the types of material that you want to make this from. So let's say titanium, stainless steel, normal steel, maybe a tool steel, various options that can be selected. And so you will get your outcomes that start to populate. And so at the moment here, we're looking at the results, those outcomes. And currently this is a thumbnail view, and we have different views to be able to display the data differently. So here we've just got a thumbnail view with some recommended outcomes, and then the first 6, well, a couple of outcomes below that as well. You can also view according to properties, so you'll have a thumbnail with properties below it. We can see that these couple of outcomes, these first 4 outcomes, are all stainless steel 440C, and it shows us a orientation, the manufacturing method. And so we can see for each one how it's made, what's the manufacturing method, what is the orientation for that manufacturing method. And then lastly, we have the scatter plot. Now in this case here, I've got the scatter plot set up with minimum safety factor on the vertical axis and mass on the horizontal axis. So we'll see they're all sitting on that minimum safety factor of 2. However, the mass gets heavier depending on the material that was used. So on the far left hand side we have titanium, in the middle we have the stainless steel, that's blue, and then on the right hand side we've got stainless steel 440. So from the scatter plot we can see which is going to be our best option, and because we chose to reduce weight, we can see that the titanium on the left hand side, we've got some thumbs ups there, that is the recommended design. So from there, you'd be able to select which one of those designs. I would go for the one on the far left. It's the lightest, and that was the goal, and it still meets the minimum safety factor criteria. So selecting that would then allow you to preview the outcome. So here we see a preview of the generated component. This looks like it would be an unrestricted manufacturing method, so we'd probably have to 3D print it. And once you've viewed the preview and you're happy with the design, generative design then allows you to actually generate and create the model. So we see here on the right hand side the outcome, the model that gets created. And I've included a little snapshot of the Fusion timeline there. The timeline is showing us that we have some solid geometry, which was the initial starting geometry that we set up. That would be those green pieces. And then the shape is actually created using Sculpt within Fusion. So that's the freeform shapes. which means that we can actually go in and edit and modify this if required. If there's certain areas that we're not happy with, we can clean them up and edit the shape, modify it, and then run a stress analysis to verify our results. And so that there is the sort of workflow and process within Fusion to go through generative design and allow those algorithms, allow AI to give us multiple options and work with those options and actually give us an editable result at the end, something we can change and work with. That gives us that solid model. We can then go through the manufacturing process to create that. Then our next example here is looking at fluid path. We have a cage valve here. And essentially this valve needs to control flow. In this case, we have the valve in a specific position to see how the fluid would flow through at that position. It has one inlet and one outlet, so the fluid is flowing from left to right in this image. And then the two halves are separated by a plate. You'll notice here that the setup is very similar to our structural generative design. We have a couple of different colors that represent different geometry, and the fluid flowing through here is water. So the next slide here, we'll see we have the same process. In this case though, we mix between fluids and solids. So we have fluid preserved geometry. These are the two ports where the fluid is coming in on the left and exiting on the right. So the green, we want to keep that fluid geometry. Then we have solid obstacle geometry. So this is now geometry that we have to have in the design. So we are seeing that we have the mounting flanges for the valve. We have a separation plate to separate the two halves of the valve. And we also then have the actual valve handle stem and the cage and ball that is going to open and close the orifice. So we need to have that geometry, but we can't have fluid in that area. So we have that as our obstacle. Then we have the fluid starting shape, that yellow geometry. This is essentially the designer's best guess as to what the cavity inside this valve should look like to have fluid flow through. That shape is what generative design will take as an initial starting point, and it will morph and adjust that shape to find the most optimum shape to reduce pressure drop through the valve. So this is the geometry setup. You would then move on to the fluid setup. So we look at the flow source on the left hand side. This can be essentially a flow rate of of fluid coming into the valve. And then on the right hand side, we have a flow opening. So that is just a place for the fluid to be able to exit out of the system. So if you had a computer case with one fan, you can have your flow source at the fan and then various openings or vents to let that air exhaust out of the case. We can also assign fluid pressures. So here we can see we have the objective where we can minimize the pressure drop, and we have limits as well. We want to limit the we want to set a limit where essentially by how far are we reducing the design volume by. So that yellow geometry represents the starting geometry. We want to reduce that down by 50%, but we want to maximize or minimize the pressure drop through that area. Just to come back to the fluid pressures, I kind of skipped over that one. On the right hand side there, where we have the flow opening, we can also apply a pressure that is required at that opening, or pressure that is applied at that opening as well. So we can have flow rate as well as pressures within the design. And then we have our objectives. So same as with the structural, we will then start the study. We'll start that study calculating. All of the information is shipped off once again to the cloud. and that calculation starts. Now in this case, I've only got one outcome. I only set up one study. And so we see here that we get the same previews. We can look at it as a thumbnail. So we can just see generally the shape. We can look at it with the thumbnail and properties. So we can see the properties. We can see the pressure drop, the volume, the maximum pressure, various information there in the properties. Or we can view our outcomes once again on a scatter plot. In this case, I only had one outcome for this. I didn't have multiple studies or multiple options to look at. We're just having a look there at the single outcome. In this case, we're looking at pressure drop on the vertical axis and volume on the horizontal axis. Once again there, you can select that outcome and you can then have a look at the preview. In this case here, the preview is showing pressure in the system. So on the left-hand side there in the image is the inlet. On the right-hand side is the outlet. So we can see as the water is flowing in, it's being pressurized, and on the right-hand side, we do have a lower pressure as there is that pressure drop. But you can see the fluid is no longer following that spherical shape. We see that as the fluid is flowing through the orifice and through the cage that the ball moves up and down in, we can see where the openings of the cage are and how that fluid flows through those openings. If we are happy with this, once again, we can generate that result. And what we get here is the same type of geometry as the structural generative design. We get a solid component that is made up of the preserved geometry regions, but it represents the fluid flow region. So this represents the cavity within that valve. And this is also, once again, made up with those sculpt surfaces or those freeform surfaces. So you can go in and you can edit that freeform and you can adjust the geometry. Maybe you don't like this hard edge here, that step. You can delete that and blend it in, make it smoother. You may find that manufacturing these cavities are going to be difficult. So you could fill those in, bearing in mind that is going to adjust or change the fluid flow. It may no longer be optimal, but you can go in and essentially change what represents the cavity of the valve or component that you are designing. You would then use this to create the body of, in this case, the valve, the geometry, the solid geometry around this to create that internal cavity. Okay, so that is the generative design side of Fusion, and where AI assists with the generative design, calculating in the background the various algorithms and going through various different iterations for your components. And the next slide that we'll go on to is showing us how AI-powered 2D drawing automation works within Fusion and how that can assist the process of generating large packs of drawings quite quickly and easily. So the data set here that I have is a Autodesk data set, this little dirt bike, the Fusion data set, and we will isolate some components or some sub-assemblies from this. But the idea here is that we are able to take the entire assembly or a sub-assembly or even just a component and quite quickly and easily generate drawings from it. So the 2D drawing automation within Autodesk, within Fusion, is powered by AI. It learns from other drawings, it learns from other dimensions that you put into the drawing, and it streamlines what is traditionally a tedious process of converting your 3D models into 2D drawings. Because normally you have to create a new sheet, create a base view, project those base views, put in all the dimensions manually. And so with this automation, you'll save significant time while also ensuring accuracy and consistency across your projects. So every time you do the design, you choose a template. That template has basically information already built into it to then create or automatically create the sheets according to sort of the style and standards that you set up in the template. So this feature allows designers to focus on innovating rather than the repetitive task of creating the same drawings over and over again. And this also minimizes the risk of error and speeds up the overall workflow process. This example here, the front end of the bike, this front assembly, front suspension assembly, should I say, 18 pages with numbering, balloons, parts lists, dimensions, took maybe 2 or 3 minutes to generate. And from there, it's a matter of going through each one and just tweaking and adjusting as needed. So just to go a little bit deeper into this brings us that error reduction. You don't have the designer staring at the screen for hours doing the same thing over and over again, potentially getting tired, fatigued, making mistakes. So by automating these repetitive tasks, AI is going to minimize the chances of human error and once again ensure consistency in the drawings. And as I mentioned, it's a time saver. The automated designs, automated drawings significantly reduces the time spent creating these detailed technical drawings. Once again, allowing the designer to focus on higher value tasks while these drawings generate in the background, and Fusion handles it and creates these drawings. The designer can move on to the next component and start designing the next component. Just before I move into the demo, I see there is a question that's come through. Has Fusion's drawings functions been improved? Early versions didn't allow for much customization of the templates. So yes, the Fusion development team has been working quite hard on improving the drawing environment. There has been quite a lot of change over the last year or two. They are pushing to improve that environment. You can customize your templates. You can add properties into your templates, into your title blocks. They've included quite a lot of sort of sheet setup and style setup, line thicknesses, your defaults for in Inventor, what we would typically call your style library. They've started to bring a bit of that into Fusion, where you can set your text height, your dimensions, line thicknesses, that sort of thing, and then save that as a company template to then use. So yes, they have been working quite hard quite a lot on improving the drawing environment. So yeah, it would definitely be worth having a look, especially with this automated drawing function. It just makes life so much easier. I actually wish Inventor had it, because it would be so much quicker in Inventor to create drawing packs. So if I have a look here, what I'm going to do is I'm going to come back to Fusion. This is actually a lot quicker and easier to demo in Fusion than go through in PowerPoint. In this case here, I'm going to do this one live. I'm taking a chance here. I'm going to take the fairings. So we've got the bike. I've activated the fairing components in this assembly. And what we'll do here is we'll start to create a drawing pack of these fairings. So if I go ahead here to design, drawings, from design, we then have in the drawings environment, in the create drawings panel here, the ability to go or change between automatic drawing creation or manual drawing creation. So I'm going to go ahead here to automatic. Below that, we can choose what is actually going to be added to the drawing. So I'm going to go select and select just the fairings subassembly. And you'll see here, it's telling me sheet count 11. So there are 11 components currently, or 11 sheets that will be generated. Those sheets are currently set to the first level of the assembly only. So we'll see frame, engine bracket 2, fairing, skid plate, rear rack, off-road dirt bike pegs, and mudguard. So those components there are top level components. They will be included in the drawing pack, and there may be multiple sheets for some of those components. If I look here, I've got 1, 2, 3, 4, 5, 6, 7, 8 components, but we have 11 sheets. So the assemblies will actually have, so the frame assembly will have a sheet just with the assembly on and a parts list and balloons. And then it will go to a sheet with dimensions. We can see here the destination. Where do we want to send this to? We can choose a template if we had a template. I don't have a template set up, so I'm just going to create a drawing from scratch. If you did have a template, you can browse and go and select the template. Then you can choose your standards if you are going from scratch. If you use a template, that standard is already built into the template, so you would not go and change your standards. You can set up orientation. I'm going to double check it's on automatic and hit OK. And that job will then start. And while that job is working, that is happening in the background. I can go ahead and I can go to the other set of drawings. The actual fact, I'm going to go to the front suspension drawings, and we will then see. So this is just quickly calculating, sending off that job. Once that job is sent off, it'll free me up to then continue on with the other drawing pack. So I'm just going to check the chat for any questions. Mikhail, if you're still on, I see you are talking about true. EA does exactly that. On the other hand, we will have a chance to talk about that. EA, just let me know what EA is. I'm not familiar with that acronym. Okay, so there we can see that job has been processed. I can go here to view job status, and we can see that the dirt bike drawing there is busy being generated. So that frees me up to go to the other drawing pack. This is the front fork, and as I mentioned, this was 18 sheets that was created pretty quickly. And so here now we can see the first sheet shows us the assembly with parts list. If I go to the second sheet, it shows now different views. We can move these around, we can edit this as we need, but the bulk work has been done. If we want more or less dimensions, we can go up to dimensions and choose auto dimension, and that will bring up the automatic or AI side of the drawing automation. So we can see we have a couple of templates, if we can call it that, and each template here has a different style. So we can look at ordinate dimensions. If I click on that, it can place down ordinate dimensions, and we can choose from where we're measuring. So we can see origin, location, bottom left. It's not giving me a very good outcome here, so I might have a look at baseline dimensions. It's not picking up a good baseline. I think this might not be the best example. So it's also calculating out here. So there's always the threat of doing something live like this is that you stand the chance of something hanging while you are busy working. Okay, so let me go ahead here. I'm going to come down to symmetric dimensions. You'll see it says 20 of 35 dimensions. So if I click on that, it's showing 20 dimensions. We have a density slider which allows you to slide left or right, left reducing the number of dimensions. We can see in the drawing we have less. Move to the right, that's going to add more dimensions to the drawing. And so you can use these sliders to customize your drawing setup. And once you're happy with that, you can click OK. And there may be some things that it hasn't quite figured out. So you are then still able to go back in after the fact and adjust and move those around. And I think that design is out of date, and that might be why this is being a little bit giving some troubles, a little bit troublesome. So let me just hit the update design there, let that update. And while we've been busy with this, you'll see that Dirt Bike Drawings V1 is ready for review. So we can open drawing there and open up that drawing. So while I've been working on this drawing, we see that the other job has been working in the background and is now completed. Okay, so while my Fusion thinks about what it wants to do there, I'm just going to double check, see if there's any more questions in the chat. Haven't seen anything come through. That looks like my Fusion has died there on that. Oh, there we go. We're back now again. So as I said, that drawing was new drawing was completed, so we can go ahead and open that drawing up, or that drawing pack, should I say. It was 11 sheets. Let that open the document, and we can see then that we will have those 11 sheets with the various views that were placed down on those sheets. Okay, so there we have that main assembly with the fairings, and as I mentioned, we've got the parts list and the balloons. If you're not happy with the balloons, you are able to shift these around. They are not fixed. You can delete and replace in if you want. We also have an option here called tidy up that allows you, or basically when you click on that, that will tidy up the drawing and recenter any views and shift dimensions and tidy them up. If I go to the second drawing here, we can see that the side view does not have any dimensions. So I'm going to go ahead and add one dimension. We would call this a seed dimension. So this dimension would be used to calculate out, or as a seed to then generate other dimensions. So let's say I want to measure a height here from the bottom of the frame rail to, let's say, top center of this cap. Let me actually just go to the top front point here on the cap. And so we have a height there. From there, we can then once again go auto dimension. That will bring up the auto dimension window as I showed previously. And we can then select the type of dimensioning scheme to be added. Now these are very organic shapes, so some of them, like base dimension, you'll see it doesn't really want to add base dimensions here. So I'm going to go ahead here. There's symmetry with ordnance. I click on that. You can see that it is adding in the various dimensions on the model. Once again, you can slide the sliders to add more or less of the dimensions as needed. Click OK. And once again, we can also use tidy up to tidy up the drawing, shift the views, move some of the spacing. While that tidies up, I see NJ's got another question. Is there a sensible way to move a relatively large assembly from Inventor to Fusion for drawing creation and then move the drawings back to Vault? Drawing automation would save a ton of time. Yeah, so Inventor and Fusion do have a link if you work with your Autodesk Drive. So over here we'll see Autodesk desktop connector, Autodesk desktop connector, that essentially allows you to save your Inventor files in a cloud drive, and you would then be able to open them from inside of Fusion. However, they would be opened as Inventor files. So that would be an interesting test then to see how the automated drawing process picks up the folder structure, or not the folder structure, should I say the assembly structure, because this works on the assembly structure in the browser. So it sees here that, you know, for this, to output these various sheets, we need to see a component or an assembly. So it will pick up the component and the assembly. So getting the Inventor design in Fusion is not a huge issue, but I think that we would have to be able to see the assembly structure inside of Fusion for the automated drawings to actually be able to output the various sheets. I actually had a customer phone me, I think it was yesterday or the day before, asking about why his automated drawings were not creating multiple sheets. It literally created one sheet, and it's because he had a single component with all of the bodies inside of that component. They weren't components in a subassembly. So it took, let's say in this case, fairings. If I expand this out and you'll see there's a whole lot of bodies inside of that, but it only creates one sheet because that fairing is a component, although it has multiple bodies. And he had that issue. He thought he had an assembly, but it was just a single component, so it was only outputting that one sheet. So yeah, the assembly hierarchy is important because that is what controls the sheet creation. So that would be something worth testing. You would put your Inventor designs into Desktop Connector, just to give you an idea here. Inside of Fusion, your projects that you see in Fusion, you would be able to access those through your desktop. Let me open up Windows Explorer here. Go to this PC, you'll see there's a Fusion drive. If I go into that Fusion drive and then access the team that I'm currently on, there's the AI, GD, and AD project. So there's all the Fusion files that I can see directly within Windows Explorer. The Inventor files would go in there and they would be visible in Fusion. Okay, with that, I'm going to jump back into the PowerPoint, and what we're going to do is we're just going to close off with a summary, then we'll open up for some more questions and answers. So in a nutshell, or to summarize, within Fusion we've got AI built into the generative design, allowing the designer to take advantage of those algorithms to generate multiple design iterations. And so this allows you to explore more options within your design, even options that you may not have thought of. And that frees up time for you to be more innovative. It allows you to spend more time creating designs that are innovative rather than trying to just iterate manually one after the other and getting stuck on just a single component. And once again, it allows you to optimize your designs. In the case that we saw, we had a bracket that existed there, but it might not have been optimal according to the weight. It was quite a heavy bracket. We needed to reduce the weight of that bracket. And then from a drawings perspective, with automating of the drawings, we're able to automate those tedious tasks of creating the sheets, putting the views down on the sheets, and adding dimensions to those parts lists, balloons. And this saves time, and it allows you to stay consistent as well. So with that summary, I'm going to open up for Q&A. I see that there have been some questions that have come through in the chat. I think I've answered those questions as they've come through already. But if I see there are still some people on the call or on the stream, if you have any questions, you can pop them in the chat and then I will answer those questions. For those of you that don't have any questions, I thank you for your attendance and the communications in the chat. And yeah, that would be it from a presentation perspective. I do have these designs I can open if there were questions about the generative design or the fluid flow design. I can open those up and we can have a look at that. See, there are one or two people hanging on to the webinar. Once again, just give a few minutes for any questions to come through in chat. If nothing comes through in a few minutes, then we will close off the webinar. Okay, I don't see any questions coming through. Once again, thank you for your attendance. This was a Autodesk webinar brought to you by Micrographics. I was your host, Carl van Rooyen, application engineer with Micrographics. If you have any questions or queries, if you have watched this after the fact, if you've watched the recording, please feel free to contact us, info@mgfx.co.za. You can also go to our website, mgfx.co.za. And thank you for watching. And please like and subscribe if you did enjoy this. We do have live webinars quite often on our YouTube channel, both in the manufacturing as well as in the architectural spaces. So feel free to browse our channel, have a look at any of our old webinars and our up and coming webinars. Thank you all and have a good day.